Okay, so we learned what a mole was, and we've learned that that a mole is going to have a mass that's equal to its atomic mass in grams, but we still haven't really figured out why that's important to us. And really, where it's particularly important is with something called stoichiometry, when we finally start to write out reactions. So first, before we jump right into it though, I want to do a little bit of review here. So we have reactants. We're going to draw a line to indicate that a chemical reaction has happened, and then that's going to produce our products. So everything to the left of this here, where the arrow is coming from, are our reactants. Where it's going to is going to be our products. And I want to make a distinction between subscripts and coefficients. So when I write CH and a subscripted 4, this means that I have a carbon and it's bonded to 4 different hydrogens. Okay. Now when I write H2O, I mean that I have an oxygen that is bound to 2 hydrogens, okay? But when I write this coefficient out in front of it, 2, that means I have 2 of these different molecules, okay? So this is telling me how many of the molecules I have. This is giving me an indication of how they're bound together. What is a single unit that is all bound together? Now, if I combine that together into a reaction, I get something like this. So I get CH4 plus 2 diatomic oxygens is going to go to CO2 plus 2 H2O. This is a classic combustion reaction. We're adding oxygen to fuel and we're producing carbon dioxide and water. So what this means is I have my CH4 plus 2 molecules of oxygen. I'm going to produce a molecule that looks like this here, and 2 water molecules. Now the important thing to remember is, why do I have these subscripts? Why is it important that there's 2 of these and 2 of these? That all comes down to our mass balance. All right. If you notice, there's 1 carbon on this side and there's only 1 carbon on that side. We didn't add or remove any carbon atoms. We didn't create matter or destroy it here. We have 1, 2, 3, 4 hydrogens. We have 1, 2, 3, 4 hydrogens on that side. We have 4 oxygens, and we have 1, 2, 3, 4 oxygen atoms on that side. And all chemical reactions have to obey this. There has to be the same number of and types of atoms on one side as on the other side. We don't get to create or remove atoms during a chemical reaction. So the coefficients that we use in our chemical reactions allow us to get a lot of insight actually into what's happening quantitatively during a chemical reaction. And we do this by making what we call stoichiometric ratios. Sometimes they call them stoichiometric factors. And what these are just conversion factors between the different components of the reaction. Okay? So I can write a conversion factor between A and D that would convert D's to A's, convert C's to A's, convert D's to B's, for instance. A reaction that's written out like that has all of these different stoichiometric factors that we could come up with. Every combination of coefficients is a possible stoichiometric factor and can be used to convert just like any other conversion factor that we use. So let's take a look at an example. This question is asking us how many moles of H2SO4 is required to react with 0.25 mole of sodium hydroxide. So the first thing we need to know is what is the reaction between H2SO4 and sodium hydroxide. So here we have our H2SO4. It's going to react with 2 equivalents of the sodium hydroxide to produce this here sodium sulfate and 2 water molecules. You're going to see in some of the later pages how you go about making this equation, but I'm just going to give it to you for right now. Now, the first thing we know is that we have 0.25 moles of sodium hydroxide, and what we want to know is how many moles of H2SO4 we need in order to react with it. And we can see here that there's 2 in front of the sodium hydroxide, and there's an assumed 1 in front of the H2SO4. So that means that for every 1 mole of H2SO4 sulfuric acid that reacts, we're going to be reacting 2 moles of the sodium hydroxide. I'm just bringing down their coefficients, and I'm labeling them as moles of the reagent. And I'm writing it in such a way that when I have the 0.25 moles of sodium hydroxide from the thing, I'm going to be able to cancel the moles of sodium hydroxide. And I'm left with the moles of sulfuric acid. When I do this math out, I get 0.125 moles of sulfuric acid. When I do my significant figures, I need to round that to 0.13 mole of the sulfuric acid. So in the last problem, we were able to answer the question of how much of another reagent we needed in order to react with a certain amount of one reagent. But we can also answer the question of how much product is going to be formed. And this is something we're usually very interested in. How much of something can I make with what I have? So the question here is how many moles of silver chloride would be formed from 0.980 moles of silver nitrate with an excess of calcium chloride. And this is important, this excess part. We're going to learn about that in just a little bit here. But what that means is that we're going to assume that we have as much calcium chloride as we need to react with the silver nitrate. And that we're going to have so much of this that we're going to be able to convert everything over to silver chloride and silver calcium nitrate. So all I need to do is build up my stoichiometric ratio here. And I start off with the information that I have. I know that I have 0.980 moles of silver nitrate. And I need to know the amount of silver chloride. So I will come up here and I will grab the coefficient for silver nitrate. And I will put that down in the denominator so that I can cancel my moles of silver nitrate. And then I will grab the coefficient for the silver chloride, the thing that I want to know. I'll put that up in the numerator here. And then I can see that I will produce 0.980. We can write in I should have had that, but moles of silver chloride.